And I will also give a brief introduction of yours. So we have Dr. Amit Reza, who will be teaching us 5 lectures. He will be giving 5 lectures on otherwise very vast topic on mathematical and statistical methods, which are useful for doing not only theoretical physics, but also for experimental physics and especially the data analysis. Wherever you have got big data, then you have to apply those methods. So Dr. Amit Reza, he did MSc in mathematics, MTech in bioinformatics from NIT Bhopal, and then PhD in gravitational wave astronomy from IIT Gandhinagar. He finished PhD in 2021. And after that, he has been in Nijmegen, Netherlands for his postdoc. His research interests, as I told you, they vary from numerical methods to bioinformatics to astronomy, statistics, computational statistics, and so on. So let's welcome Amit. Over to him.
Yeah, thank you, sir, for that nice introduction. And yeah, I'm very happy to give a lectures on this specific topic. So I'm not sure like how many of you already are aware of this specific topic using Python. So before going to start my presentation, maybe it will be nice for me to understand what is the understanding of the Python, at least from the participant perspective. So can I just ask like how many already aware of the Python programming and at least did some basics Python program coding using during your any courses. So if you are use Python for any of your exercise, anything, just in the chat box, can I just write yes so I can count? Okay, so okay, so how many are, so I just say how many students are there? I think almost 8, right?
Yes, Sri Lakshmi has a hand raised. Yes, Sri, please go ahead. So people are saying they are familiar with Python.
Okay, so it's good. Okay, so it's good that you already familiar with Python. So actually, I was not assured that I was not sure that how many already know about Python. So what I did, I thought it's better to divide this whole 1 hour lecture into 2 parts. First part is some basic exercise in Python, and second part is discussion on a specific topic that is called linear regression. So since you already aware of the Python, so maybe I can switch in other way around. So I'll start with the first lecture on this linear regression and try to give some example in Python for this linear regression. And if we're able to finish it, then probably you can go to some other topic, which is not maybe right now is required, but if you're going to work on some large data, then basically you need to learn the Panda, because you need to describe the data frame or the data in a nicer way. To represent data in a nicer way, you need to use Panda data frame. So today I'll try to cover at least to cover 2 topics. One is linear regression and another is basically Panda data frame. So this is the topic I'm going to cover today. So now I'm going to start my presentation. Thank you for that information. Okay, so hi everyone. So as I already mentioned that I'm Amit. I'm a postdoc, currently I'm a postdoc at NICEF Amsterdam. So today, during this whole 1 week, I'll try to cover these topics, the mathematical and statistical method in Python, right? So as you know that the title is saying that basically we need to cover 3 topics. The mathematics part, what are the mathematical methods we are going to use to solve any problem, either it is a problem of physics, or either it is a problem of biology, or either it's problems of computer science. Anywhere you need to use some algorithm or need to design some algorithm, need to solve some problems using some numerical methods. So you need to know what kind of mathematics actually you need to learn to solve this kind of problem numerically. So that is one thing. Second thing, statistics, because these days people are actually working with the data, right? So either you are working with astrophysics, either you're working with some particle physics, or you're working with some other physics domain. Everywhere the data is available, and there is a rich big data. So directly like analyzing the data is not possible until unless you are implementing or applying some statistical method. So it's very crucial these days to understand the statistical method. Now there's a two way we can understand those statistical method, maybe theoretical way, right? But to give a proof and validation, you need to also show those results. Those theoretical calculations can also be validated through your numerical analysis, and for that you need to learn how you can do a statistics over using some program language like Python. Maybe you can also pick up some other languages like R or some like MATLAB, but right now we are going to focus in Python, because if you're able to learn Python properly, then you can also write code in MATLAB and as well as in R. So these are interfaces similar. So learning one can actually help you to improve the learning of others. So better to stick in that way. So during this 5 days lecture, what are the topic in broad sense I'm going to cover? So so first of all, in mathematics, there are vast of topic, right? So those who know that in maths there are several topics which are actually relevant for mathematics student, but in terms of the numerical analysis, or in terms of data analysis, what are the topics are more important in the context of physics, at least the linear algebra, differential equation, and numerical method. So these are the 3 topics which I'm going to cover. Regarding statistics, I'm going to cover the regression analysis, though this regression analysis actually is directly related to the mathematics. So today I'll just try to cover one specific topic in regression analysis, that is called linear regression, and I'll try to give a understanding how this linear regression actually connected in terms of mathematics and statistics. And then obviously there is the specific topic that's called distribution. So there are different distributions which you need to learn, and their representation, their visualization, and why it is important. Second thing, and one of the very crucial topic in statistics is the Bayesian analysis. So I'll try to cover some understanding of Bayesian's analysis in terms of Bayes law, and try to also extend the whole analysis, how we're going to implement the Bayes law directly for a numerical analysis or numerical simulation using some like sampling technique like MCMC. So those are the topic which is the little bit advanced. So I just try to connect in such a way that today, since the first day, I'll try to give some basics problem or basic example on linear regression, which will maybe start of this journey. But in the midway, like Tuesday, Wednesday onwards, I'll try to cover some intermediate topics like Bayesian analysis and multivariate statistics, because when you're going to talk about the data, the data is not depending on only one variable. It can be depending on several variables. So rather than focusing on single variable statistics, it's better to also focus on multivariate statistics. So I'll try to give that notions also. So these are the part which is very crucial in terms of math and statistics that I'll try to cover. Now, in terms of implementing those algorithms, models, or numerical schemes using some coding programs, for that we need to going to use some Python package. And for that, what are the topics we need to cover? NumPy, SciPy, Matplotlib. These are the very basic topics. So I'm not going to cover, because most of you already know how to use Python, right? So whenever I'm calling some specific function from NumPy, SciPy, Matplotlib, maybe I can directly introduce, or I can describe about those functions at that time. Otherwise, I'm not going to cover this NumPy, SciPy, Matplotlib. But those who are already not have not used this Python package before, for them the starting point should be NumPy, SciPy, and Matplotlib. So NumPy, SciPy is for to represent your data, or like your variables in a list and array. This kind of understand, you need to understand. SciPy actually normally used for some mathematical operation like matrix multiplication and then inverse, all kind of thing. Matplotlib is normally used for basically to represent your plot. So if you want to make some good plot, you need to use the Matplotlib and as well as Seaborn. So these are the two packages which normally people use for the visualization. And there is this advanced topic which is called scikit, sklearn, and Panda. which I think better to cover. So I'll try to cover scikit-sklearn, and scikit-sklearn I'll cover because whatever the topic I'm going to cover in mathematics, for showing some examples for those approach, I need to use some specific function from scikit-sklearn. And as I said that right now we need to also understand how to handle large data. And for that, the data visualization or data structure representation is very, very important. And that we can also do with Panda. And that I'll show today. And lastly, the object-oriented programming. So yeah, I think those who already are aware of Python coding, you can write your like any problem in terms of some function and as well as class. So we'll try to cover some example where we actually build our own function and own class, and this can actually help you to understand what is object-oriented programming. So these are the topic which I think very, very crucial at least for the beginners to cover up. And there are two other boxes you can see in the red mark which I did. That is machine learning and the time series analysis. So though this is like integrated part of the whole analysis, I don't know how much I can cover, but actually I want to cover this machine learning topic because this is a hot topic in data science domain, and people actually using machine learning for solving some physics problem as well as some other domain problems. So if you really interested to work on some computational problem, so better to learn this machine learning topic. Actually, this machine learning topic is a part of a computer science, but normally as it is implementing on some data, so therefore it is a very open topic for any domain. So I'll try to cover some concept, at least what is supervised learning, unsupervised learning, how machine learning is connected with mathematics and statistics, clustering, classification, deep learning, those topics. And if I get some time, then probably I'll talk about the time series analysis. This time series analysis actually is important for those who are actually going to work probably in the upcoming years in the astrophysics. Whenever you need to analyze some time series data in astrophysical sense, then actually this kind of representation, signal processing, basic signal processing, how you're going to use some statistical approach to solve those kind of problem, what kind of problem you can solve in terms of forecasting, classification. There are different kind of problem you can solve in that way, and how you're going to use classical statistical approach or machine learning approach to solve this kind of representation. So that is the crucial part, but I'm not sure either I'll be able to reach up to the time series analysis or not, but definitely I'll try to cover these 4 different models which I already discussed. If I'm not able to cover this time series analysis, at least I'll request all of you, if you interested, go and check this topic also. Okay, so any questions regarding this slide? This little bit bigger slide, because I just try to give what exactly I'm going to cover within this 5 days workshop from my side. Any questions? If there's any questions, just let me know right now. I can break it in again, or I can say it again. Anything? No,
No,
right?
sir.
Okay, thanks. Okay, so as I said that today I'm just going to cover the very basic topic that is called linear regression, right? So I don't know how many of you already aware of linear regression, but let's say at least during your courses, maybe you already covered some topic that's called curve fitting, right? That you have some profile which has some specific value at different ranges, and you want to see how actually the behavior of those kind of curves. So ideally, you can say that, okay, a curve can be represented in terms of higher order polynomial, so that is basically second order, third order, fourth order. But as I say, if you consider the first order, that is a linear regression or linear curve fitting. So whatever I'm going to talk about in terms of linear regression, that is equivalent to talk about the linear curve fitting. So basically it is fitting of a straight line. So I'll talk about today how to fit a straight line for a specific data set, and how kind of intuition you can get from that. So before going to talk about this straight line fitting, or in the layman's language it is straight line fitting, but in proper language it's a linear regression. I'll just try to give why this topic is important, at least for those who are going to work with the data. So in data science domain, normally when you're talking about data, we have some specific representation, right? That means that for a specific problem, we have some set of variables, and for that we need to see what kind of representation that data actually gives, and we try to come up with some understanding about those data in terms of some hidden information, right? So whenever we're talking about data can be represented or visualized using your linear algebra. So linear algebra can be used as a tool to represent your data. So when I'm talking about 1D data, that means basically you have only one variable involved, right? So you can see when I wrote x equal to 1 here, that means you're using some one variable, that is x, and that is fixed, that is a constant, right? So in a vector space, it is just a point. In a 1D vector space, it's just a point, but it's a fixed point, right? Whereas when actually I wrote this, okay, x plus 2y equal to k, this is actually a it's a two-dimensional representation of a vector space, because it has now two variable x and y, right? But it is not a fixed point, right? The direction of that vector can be changed based on that parameter k. So here you can notice that there's a two different representations there. So one is variable, so we have a two variable x and y, that's why it is in 2D. But there are also another parameter, that is k, right? So if you change k, then your direction of that this vector can also be changed in terms of solution, not in terms of representation of x and y, because the way I've shown x plus 2y, if you represent x plus 2y in a vector space, that is basically 1 and 2, that is fixed. But when you change that k parameter, the results of, or the what is the outcome of that vector can be changed, right? So solution can vary based on the parameter. So whenever I'm going to talk about in the upcoming days variables, that means basically to visualize the data or to represent data, and the parameters which I'm going to talk about, basically they're actually going to handle or going to control the whole system. So this is sort of representation. Now I think scalar vector, those things is very common, very well known in physics, right? So there's no point of talking on that part, right? But this vector concept is directly related to your system of linear equation. When you're going to talk about, okay, I have two different vector, right? And these two different vector can be represented in the same space by, let's say, this example, x plus 2y equal to k and 3x plus 4y equal to q, right? Now obviously 1 and 2, this is one vector, and 3, 4 is another vector, but they combine together and they make a system of equations. And there are two parameters, k and q is involved, and for that you might get some two different solutions, right? So this representation is actually is called a system of linear equation, because this relation x plus 2y equal to k is a straight line, and similarly 3x plus 4y equal to k, this is another straight line, right? So you can say it is one system, linear system, and the second one is also another linear system. So it's basically making us a family of linear system, and that's what it's called, system of linear equation. Now if you write this system linear equation in terms of metric representation, then how are you going to write that? Basically whatever the coefficient of your x and y for the first case, that is the first vector, that is 1 and 2, that is written in row, you can see here. And then similarly for the second equation, that is 3x plus 4y equals to q, that is also 3, 4. So this is a metric representation for this system equation. It is shown by this a, and this small x, basically the vector which actually contains all your variables, and this b is the vector which contains all your parameter, right? So I can say whenever you have some specific system for which you can write your system equations in terms of some coefficients that actually shown by the visualization of your vectors in the vector space by this matrix A, like that, and you have the one small x vector that contains all the variables, and b is the vector which contains all the parameters, right? So if you have a let's say three variables, then basically the dimension of this x vector becomes 3 in 3, and the vector the dimension of b vector becomes 3, right? So this is a simple representational this simple represent of system linear equation, right? Now I think up to this you already aware of, because I in your several problem, maybe you already solved this system equation, right? Now can you please tell me what should be the solution of this system equation? Anyone know how to solve this system equation? Anyone? Does it make sense?
Yes, somebody said Cramer's rule, symmetric inversion method.
Yeah, Cramer's rule, right? So when you're talking about Cramer's rule, that basically you're saying that okay, we need to use some matrix inverse method, right? But how you know that this matrix inverse can be worked here, right? So yeah, those like who already gave the answer, that is the correct answer. So I'm going to explore that direction. Okay, so up to this, I think all of you are aware of the representation of the data in terms of the matrix. But there is another concept which I'm not going to cover in this topic because that's a little bit advanced topic. That's called a tensor. This tensor representation is a little different from the physics way. It is the tensor representation for the data, where actually you're not going to talk about only a system equation for a one specific problem, but you have a same problem, but you have a two different representation, and you need to need to save or need to visualize both the representation together. So if you have let's say if you have several representation system equation like this, let's say a1 x1 equals to b1, similarly a2 x2 equal to b2, then basically you have two different vector space which actually is replica of the same problem, or they are actually combined together to solving a same kind of problem. It's like sort of a manifold where you're not representing your space in terms of only one layer. You need to think about there's a two different layer and they are connected in some sense. That means there's some correlation between these two different system equations, and they are connected by these variables x and y and the parameters. So if there are some correlation between these parameters, then basically we can't solve this this problem in terms of a matrix representation and independently. So in that case, what you need to consider that okay, the parameters, this k1 q1 and k2 and q2, they are also correlated. And to understand that correlation, basically you can actually represent in terms of the tensor, and you need to use some multivariate statistics to understand what kind of correlation is like present in between those parameters, right? So in simple sense, if I assume that this k1 q1 and k2 and q2, they are independent of each other, then basically it's actually two different system of equation and they are independent, so they are not connected, and that sense it is only a matrix representation. But when I'm going to consider that okay, k1 k2 and q1 k2 are related, and there are some correlation exists, and in that case you can't actually consider them independent, and for that you need to find out what is the correlation between these two different system equations, and that can be actually represented as a your tensor. So that is another important aspect. So when you are going to talk about some like complex problem, in complex problem, whatever the parameters we're going to consider, they might be connected because they are coming from some specific statistical distribution. So in that case, there might be possible that the correlation is already present, and you don't know what kind of correlation is there. So from data analysis, in perspective, you need to understand what kind of hidden distribution actually is responsible for that kind of represent of this kind of parameter, and that the thing people normally try to understand or identify using this tensor representation. Okay, so I think I already gave this little basic understanding and visualization of this matrix representation or this the whole system equations. Now this linear algebra actually is the basic tool to connect your probability statistics and the numerical methods and the machine learning and deep learning in the context of when you're going to write a code, right? Because maybe in math in the sense of ax equals to b, you can directly solve using your pen paper, right, directly over your copy. But when you're going to solve in a coding language or in a computer, you need to actually, whenever you're solving some statistic problem or numerical methods or whatever, you need to actually first represent your data in terms of some matrix representation, and that's why matrix representation is important. And once you're talking about the matrix representation of data, then basically you're directly talking about the aspect of implementing the basics concept of linear algebra, right? So probability statistics, numerical methods, whenever you're solving some new problems using some numerical schemes, or you're designing some new approach or new solution, always this linear algebra is coming as a byproduct. because you are representing your data in terms of some matrix representation or vector representation, and from there directly they are connected with the linear algebra. So whenever you're talking about any other these three topics, they are actually connected to the linear algebra, and linear algebra is the first block which people should learn, and should through it should connect all the other blocks. So this is very important, and there are several examples where actually it can be used. So starting from computer vision, astrophysics, bioinformatics, network science, NLP is natural language processing. Maybe these topics are not aware, like all of you are not aware of this topic. At least astrophysics aspect you already aware of. So there's so many other fields where actually you can implement linear algebra. So whenever you are actually going to solve some data, this linear algebra is coming directly. Okay, so I think I gave very brief understanding about this linear algebra, importance of linear algebra. Now I'm going to talk about the regression, right? So regression can be several ways you can think about regression analysis, right? So one way is that, okay, in very layman language, okay, I am going to fit a straight line, and I want to know what is the slope and what is the this intercept. So in that case, I just want to know the value of that specific at which this straight line is going. I just want to know at a different point what is the value of that specific straight line, right? So that is basically just a simple way of understanding, okay, I have a straight line in a 2D space, and I just want to know what are the point which actually satisfy that straight line. So basically you're going to solve a system of equations in considering that, okay, I need to find out some points at which actually satisfy that system of equation or that straight line. But in actual sense, that is basically nothing but the predictive model, right? So basically you're going to predict something or predict some value after fitting or after getting that regression analysis, right? So let's say from this plot, so you have some data points here, right? So you can see there's the blue dots actually showing some data representation to this space, and this straight line is a fitting. So let's say I have some linear regression algorithm by which I can fit this data, and then what I can say, okay, if I want to know what should be the value at, let's say, this point, right, then I can directly go to that point and see what should the value, and based on that I can say, okay, the value should be like that, right? So this, in that sense, whenever you're going to identify some unknown like value at some unknown point, that is basically the prediction of some specific model, right? So regression analysis is very useful when we talk about prediction. And so whenever you have some model, you are generating some data, you just try to understand what kind of prediction I can make, and for that the basic task is to do some regression. So now now probably from this plot it is also clear that since these dots are not actually in a straight line, so though you actually fit with the straight line or the linear regression, it is actually not giving a good fitting, right? So in that sense, basically this fitting is not good. but for this data, this is the best linear fitting you can get, right? So maybe for that you might not be, the linear fittings might not be the optimized solution. So what you need to do, you need to pick some nonlinear regression, right? So nonlinear regression is basically the higher order polynomial fitting in terms of adding some more polynomial terms, like second order, third order, fourth order, right? So there are different kind of regressions are available, and so basically you can describe, or you can categorize the whole regression in terms of linear regression and non-linear regression, right? So for some data, maybe linear regression gives a good solution, but for some data where data is very complicated or very complex like features are involved, so then maybe your straight line fitting is not good enough, and need to talk about some non-linear fitting in terms of like polynomial regression or logistic regression or some different regressions, right? So these are the different way you can think about implementation of regression. Now regression can also be different in terms of, as I said, that for statistics perspective, you have a multivariate statistic and you have single variable statistics, right? So single variable statistics, if you think about, I have a system where only the one variable is involved, so then this is a single variable statistic, and then you can do a single variable regression. Whereas for the multivariable representation, you can use a multivariable regression. So these are the different way of looking into the problem of regression in terms of what kind of category you are going to solve. And as I said previously, that normally when you're talking about data for this kind of fitting, you need to think about what are the number of independent variables, So I already talked about in the previous slide the variables and the parameters, right? So when you're talking about the regression, you need to understand what are the number of independent variables and what are the number of dependent variables, and what kind of shape you are actually looking from the data visualization, and based on that you can decide either you're going to do a linear regression or you can do a like higher order regression. So here you can see that obviously x-axis always represent independent variable, and the y-axis represent the dependent variable. So this is the simple understanding how you can use the regression as a block structure in terms of different way of looking into this problem. And now where you can use the regression, you can use the regression for the forecasting of a time series modeling. You can use to do a classification also. So we'll look into those things right now. Okay, so I think I gave already very brief understanding of regression. So I'm not going to talk about the more theoretical part, but what I'll do, I'll try to give some example over Google Colab and try to run it as well, right? Simultaneously, such that you can understand what exactly is going on. So let's say we're going to talk about this problem in terms of the Google Colab. So we have some linear regression problem where actually we have a two variable, right? The one is the basically area. So this is basically the price of a house. So if area is this 2,600, 3,000 like this, then basically the price is increasing in this way, or this is the different prices based on different area, right? So here obviously independent variable is the area and dependent variable is basically the price, right? So now the question is, if I want to solve this and I just want to understand like for some, let's say for a specific value, like 3400 square feet, what should be the value? Like what is the price, right? So from this list, obviously this 3,400 is not listed in this table, right? So what you need to do into the regression, and we need to come up with the solution for this 3,400 also. So you can also think about this simple problem in terms of interpolation, right? So when you learn the interpolation, you know that okay, you know what is the range of variables, and in that range you can do an interpolation to get back the value at any point in between that, right? So basically as I said, that this is straight line fitting. So you can think about, okay, I'm just fitting a straight line. That is the y is basically the dependent variable. This is the price, and this xw plus b is basically x is the independent variable, and w is the slope. Like what is the in 2D space, what should be the direction of this straight line, and b is basically what is the like intercept in terms of from the origin point. So if you're able to find out this w and b, then basically you can directly solve for any problem, right? So you can plug in any x here and you can get back what is y. So here basically you are going to solve a straight line problem considering this w and b as your solvable thing. So basically if you write in terms of this matrix form, then it is nothing but ax equals to b to solve wab. So this x vector should contain w and b, and a should contain this coefficients, right? Okay, so does it make sense? So if it makes sense, then probably I'm going to directly to the any question. So if there's no question, then probably I'm going to talk about directly to the regression problem. To give me this a minute.
Sir,
yeah.
In a experiment, in real life experiment, do we have to use do we have to use coding as a physicist?
Yeah, like if you're working with a theoretical, there's a two aspects. First of all, if you're working with some theoretical physics problem, then also you need to learn coding, because at least you need to validate those theoretical like problems with some representational validation, right? So for that validation, you need to do some kind of plot. So for that is obviously required. But if you're working with a computational physics, where actually you need to handle large data, then basically these methods you need to learn, because you can't directly solve those problems using some theoretical understanding. You need to solve considering some numerical methods, and you need to, since you need to handle large data, directly looking to data is not able to understand what exactly going on in this data. That means you don't know what are the relation between those variables, parameters. So it is very complicated way of looking. Let's say I have a problem where 1,000 variables are involved and 1,000 parameters are involved, right? So obviously by hand it is very difficult to solve. Right now, obviously for this example, I'm showing a one variable or the two variable only, right? But ideally, in the practical sense, when you're going to solve a computational physics problem, it might have 100-dimensional vector space. It is not in 2-dimensional vector space, right? And we have a limitation that after 3-dimensional vector space, we're not able to visualize the data. So it is itself a problem that how we're going to visualize the data in the higher dimension in terms of 4, 5, 6, 7, 8, 9, 10. And if you're not able to visualize it in the high dimension, it's very difficult to understand what kind of information it has. And for that, to basically to get back those information, you need to use some numerical method by which you can actually express them and try to understand what kind of relations they have. So definitely coding is required for computational physics. The coding is very, very important because you need to solve all the problems using your coding, as you need to implement your numerical methods using some language. But for theoretical physics, at least you need to know how to make a plot between your results. Yeah, for some theoretical problem, you need to also solve some very complicated differential equations that might not be directly possible to solve using your theoretical way of solving a numerical differential equation. For that, you need to also to solve the theoretical solution of those kind of theoretical problem using a specific language that is called Mathematica. So there's Mathematica is another language at which normally theoretical physics is used to solve some numerical problem or theoretical problem. So there are different coding language which you need to learn to solve. So coding is important right now for the research. Is it fine? Okay. So for the same problem, as I said that if you have a data, I can directly represent that in terms of the matrix, right? And one of you already said that, okay, if I know that, okay, that is basically a system equation in terms of AX equals to B, or here is basically AW equal to Y, then basically you can get the solution in terms of W equals to inverse of Y, right? So that is the Kramer rule, I don't know who told that, but give us sort of an answer for that, right? So now I just try to show this. Okay, so for this example, what are the packages we need to incorporate here? So first of all, NumPy, because whatever the variables you're going to define, that should be defined in terms of some array representation or vector representation, and for that we need to call some array from the NumPy package. So we are importing here NumPy, right? So we are importing NumPy as NP here. Similarly, you need to visualize data, so we need to import matplotlib.pyplot as PLT. And then we need to also incorporate a specific package, SciPy. Basically, it has directly solvable. It is a linear algebra package. So linear algebra package at which you can directly call some inverse of a matrix. So whatever the matrix or whatever the linear algebra operation is possible, all are actually is available here. And then there is another package that is called sklearn. There are already inbuilt. There is already inbuilt a function called linear regression. So you can this is basically this function is actually part of a class that is called linear underscore model. So you can directly call that linear underscore model class, and from there you can easily use this function linear regression to solve your problem directly. And there's some measures that is called sklearn matrix, but from which you can actually estimate what are the error you are getting. So these are the different packages which is required to see this problem. Okay. Now, as I already said that for this example, we are going to show that what exactly the results, right? So these are the values of the area, and this is the values of the price, right? So I just wrote x equals to those. This is basically x equals to area, so I can just change it area, right? So I can change the price. Okay. So anything regarding this packages? No, right? So so these are the variables for which we're going to solve, right? So now you can see that this is area. Okay, so you can see that these are the values I already wrote it here, right? So it's very easy to understand. But if anyone has questions, please let me know. So now after that, what I can do, I just plot them, right? So it's just a simple plot. So I'm using as I said that I'm using a matplotlib for the plot, right? So I can use as I call it as a PLT. So I'm calling, there's a plot function from PLT, that's a PLT plot, and I'm plotting what area and the price, right? And I'm just marking them as a dot value, and I'm just calling them as red. So if you do that, then basically you'll see this is the value you're getting. So for different area, you're getting different prices, right? Now, as I said, that I need to solve this problem, right? So I will try to show that, okay, you can solve this as a matrix problem itself using a linear algebra concept by taking the inverse of the matrix. And you can also solve using the package, and we'll see which one is giving a good answer, right? So now I just, I need a AX equals to B representation. And for that, what I need first that A matrix. So obviously to make that A matrix, first I'm just making a two-dimensional matrix space. Basically, this is basically, so it is length of the area. So you can check, right? So this is, you can check what is the shape, right? So if you check the shape, so it basically 5,2, right? Because you have all the 5 values of area, right? And second column is basically the price, right? So it's basically this structure. So this structure. So 1, 2, 3, 4, 5, the 5 rows, and it has 2 columns, first column, second column, right? So this is showing that, okay, this is a matrix representation. It has 5 rows and 2 columns. Okay, so now I need to plug in, I need to provide the values, right? In the first row, it should be the values in terms of area, right? And then second row, it should be okay. So now just to think about, so when you're solving this system equation, you need this A matrix, right? And this A matrix should contain all the variables. The first variable, the independent variable, that is the area, the value of the area, and second column is basically the 1. So you can, if you see this representation, from this representation, it should be 1. So that's why I made a matrix A which has all the values of this row and columns is basically 0, and then I just incorporated the value of this area, and the second column I just made 1. So that I already did here, right? So you can see this is basically the value of the area, and this is basically the 1, right? Now there is a simple concept that, okay, since when we can do a inverse of a matrix, when it is a square matrix, right? Or you can say that whenever inverse is possible, right? So you can see, since the dimension of this matrix is basically 5,2, and it is not a square matrix, right? So for this matrix, you directly can't do an inverse. So what you can do, you need to understand how I can solve this problem, right? So ideally, the solution should be A inverse of y, right? If I'm solving these system equations in terms of AW equals to y, right? Then solution of W is nothing but A inverse of y. Ideally, this should be solution, but this solution is only valid if actually A is a square matrix, or it is inversible. Inversible means basically determinant of that matrix is not equal to 0, right? But it is in theoretical sense. But in practical sense, for data, it might be possible that it is not a square matrix, which is perfectly possible. And for that, you need to understand how you're going to solve the problem, right? So for that, what we can do, we can multiply both sides. So for this equation, we can multiply both sides by A transpose, right? So if I multiply both A transpose, basically it's become A transpose A into W equals to A transpose Y, right? And now you can see the dimension of this matrix is become basically 2 cross 2, right? So now this A transpose A is basically a square matrix, right? Now I can take an inverse of that because it is a square matrix. And so then the solution should be A transpose A inverse into A transpose Y, right? So rather than taking this as a solution, what we are considering this is as a solution, right? So whenever you have a matrix which is square, you're going to take this as a solution, and whenever it is a non-square, then basically it is your solution. Does it make sense?
Yes, sir.
Okay, so this is basically, this is not a inverse of a matrix, but it is sort of called a pseudo inverse of a matrix. So if you want, you can go and learn a little more about pseudo inverse, and but anyways, that term is not, doesn't matter. The definition of pseudo inverse is like this. So this is which we need to do for our case. So what we did here, that okay, first we need to multiply A transpose both sides, right? So I need to construct a matrix which has basically A transpose A. So that's why I define a new matrix, that is B1, which contains A transpose A. So it is 2 cross 2, right? Now as I said that this matrix should be 2 cross 2, so it's become 2 cross 2, that b1 is become 2 cross 2, that's fine. And now you need to also check what is the determinant of this matrix. The determinant of this matrix should also not equal to 0, otherwise you can't take an inverse of that, right? So but it is obvious after taking that it will be a non-zero. So determinant of that matrix is non-zero. So if you take the linear determinant of that matrix, so I am calling the determinant of the matrix from the linear algebra package from the sklearn, right? So this actually shows that okay, this determinant is non-zero, so you can directly take the inverse. So now I'm taking the inverse of this matrix, and that's basically shown here, right? So inverse also 2 cross 2. Now the final solution should nothing but is basically okay, so this is B inverse. Okay. Yeah, so now you can say I need to multiply with A transpose also, right? Because now this is basically the B1 inverse, and then I need to multiply with A transpose. So that's actually I define as B2. Okay, so now you can see the dimension of B2 is basically 2 cross 5, and it is expected because this one is 2 cross 2. This one is 2 cross 2, right? And this one basically is 2 cross 5, right? So then it's become a 2 cross 5. Okay. And now basically solution nothing but this B2 into Y, right? And that means this B2 is basically is nothing but A transpose A inverse into A transpose and then the Y, right? So then it's a solution. Oh, whatever. Okay. What is length of Y? Y is the, just a minute. Oh, so that is price. Sorry. So I changed the variable name. So it was taking the previous variable. So it should be price, right? Now you can say this is a solution, right? So this is basically a solution. So you're getting some specific the slope and also the intercept, right? Does it make sense? Now, how are you going to use that solution? So that is the one question. Yeah, go ahead. Hello? Any question?
No questions.
Sorry, I can't hear you. So if you have a question, just write in the chat box. Probably I can answer it later. Okay. So that way I was talking about, so then maybe I can directly see. Okay. So once you have that solution, you can directly get the value at which point you want the solution, right? So the same thing, the way actually defining here in terms of this whole thing, A transpose A inverse into A transpose, that is equivalent to, as I said, that is a pseudo inverse, right? And that pseudo inverse directly can be called from a package called linear algebra. So the linear itself is has a specific function called the P inverse, and that directly can be callable. So you know, to the way actually I have showed, it is basically, maybe if you write your own code, you can do in this way. But if you don't want to write your own code, then basically you can directly call in this way, and you can get the solution also. So if you do the same thing, so basically the solution is basically a two-liner. So, right. So now you can see this is basically I used whatever the packages, whatever the functions available in those packages, and that will solve me the same solution. Right? You can see the first solution one is actually our approach using directly linear algebra concept. And this is basically the second approach is basically using some packages or function, inbuilt function from that packages. So you can see both the results are the same. So that means the way we define the pseudo inverse and the way they are calling that function pseudo inverse from that specific package, they are actually giving exactly same solution, right? Now, this is your slope intercept, and you can easily predict the value. So for these two data points, basically this is the best fitted straight line you're getting. And whenever you need the solution for this point, you can directly call that and you can get the solution. Now, I'll just talk about one more topic in this here. Okay, so fitting of a straight line makes sense, right? I hope so, right? So now the point is you need to understand what should be the, so if you go through this, actually you can see that this is the representation I was talking about and you can get the solution, right? So I already showed this thing, you can go and check it. Okay, so you need to understand one more thing, that is basically the error term, right? So the problem is that you can get different, like let's say there are three people actually solve the same problem and they are come up with three different straight lines for fitting the same data point, right? So how you can say that which one is giving the best solution, right? So what you know that, okay, whatever the point you already know the value of y, the value of those point you already know, you can plug in those value and can see what is the error you're getting, right? So you know the value at y1, y2, and y3. Now for these three different solutions, what you can do, you can find out what is the actual value and what is the predicted value, right? So this y1, the blue one, is the actual value, and y1 cap is the basically predicted value. So you can find out what is the distance or the difference between these two solutions, and that is basically your R1, this is the residual part. Similarly for the second point, and similarly for the third point. So for all the points, you can actually find out what is the residual, considering your fitted line, right? And then actually that will actually give you the measure of your error. So you can easily estimate what is the error in terms of this specific status that is called R square, and that is nothing but basically function of your residual. So you can see this is basically the formula we're using. R square basically is a normalized statistic in terms of 1 minus your SS residual divided by SS total, and SS total is nothing but basically a difference between your given y and the mean position, and y, and SS residual is basically the difference between your observed point and your solution point, so your estimated point. So this is basically residual. So if you're getting, if you're normally, if you take the ratio of these two, basically this will give this ratio, and if you, it will be always should be in between 0 to 1, and then basically you're getting the R square between 1 minus 0, right? So this is the way we normally measure this error. So I'll just try to show this what is the R square value you're getting here. So sorry. So here it is basically the price. Right. So here we are getting R2 is basically the 0.95. So now the interpretation of this, if you're getting very if your R score is 0, right? That means basically the baseline model is good. But if R square is actually negative, it is very worst fitting. And if it is actually matched observable with the 1, then it is like best fitting. So in that case, it is not exactly 1, but it's the best one based on your given data point. So that's the way you can actually measure either your actually fitting is good enough or not based on the given data. Now the same thing, the way actually I was talking in terms of this linear algebra solving, you can directly, if you don't want to write your own code, you can directly call this linear regression function from this sklearn package, and you can directly do the same thing for the this fitting. So this is basically area, this is basically the price, and this is your solvable model, and you can see what is the solution you're getting for this. Right. So now you can say this is also same, the 0.95, which is equivalent to what exactly you are getting, right? So that means either you are calling that package to solve this, or you are actually using the statistical approach the way we did that. Both actually are equivalent and you're getting the same answer. Does it make sense? Does it make sense? Anyone have any questions?
Yes,
Okay, so now once you have that specific value of intercept and the coefficient, you can directly get a solution for different points. So you can get a solution directly, and then you can plot it. So you can see this is the plot. Sorry, this is always I missed on. So the concept wise linear regression, you see, I don't know, like probably all of you already aware of this linear regression theoretic, right? But I don't know how many already have tried with the Python. So today we just tried that, okay, this method can be also implemented through Python directly in terms of your understanding of mathematics, the way you solve the linear system equation, or you can directly call some package using from the sklearn, right? So if you write basically if you call the sklearn package, basically this is just a one-liner solution, right? Because you are actually calling here, you're calling here the function, right? This linear regression function, basically this is the data, and this this model you're calling from the sklearn, and you're getting some solution. So it is just a one-liner solution, which actually I took almost 30 minutes to describe, right? Because the behind that model, whatever way we did here, this is the maths behind that. So until unless you know what exactly is going on those function, it is very difficult to understand the results, right? So I just try to give a notion that, okay, if you understand the maths, it is very easy to understand, or easy to use some packages or some function from directly from the packages. And if you want, you can build your own function to solve the same problem. So I hope that makes sense. And if you have any questions, just ask me, because I think I have 3 more minutes. So maybe I'm not going to cover the Panda data frame, but tomorrow I'll start with that. But is there any questions regarding this this exercise? If so, just let me know. Just please just ask. We have 3 more minutes. Anything? No?
Can you share the notebooks or
Yeah, sure. I'll share the notebooks and
even the
slides.
basics ones if you have, sir. Python basics if you have made any.
Yeah, sure. I made the Python basics, so I'll
Okay.
share that.
Thank you.
also.
Yeah.
But any questions regarding this linear regression today?
No, sir. It was clear.
Okay, is it clear to everyone? But if, like, feel free to ask anything. Like, I'm not asking that you need to ask anything related to the only that exercise. Since this is the first time we are talking or we are doing something, and we need to continue for the upcoming 4 days, right? So I need to understand what kind of problem you're facing regarding this lectures or the tutorials, because I have one hour time, right? So I don't want to give only the lectures in that time period. I want to give some hands-on session, so I'll be like working in this way. So some theoretical understanding and some coding. Is it okay? Is it fine? Or I need to change the approach? What is the feedback? Probably, if you want, you can give me the feedback so that I can modify it based on your choice, and I can follow in the upcoming 4 days, right? Otherwise, like there are so many topics. If you are not able to figured out what exactly the right way of presenting all those things, at least for me to difficult to explore, or like maybe you not get that much of flavor what I want to give in this session. And I don't know how many of you actually are looking for physics problem. I'll try to do some physics problem, but for my course is basically is more about handling some mathematical statistical methods to solve some problems, right? So right now I'm not focusing on the physics problem. I'm focusing on what kind of tools we can learn, and how those tools can be useful for solving some problems in terms of writing the code and try to understand those problems individually. So just let me know what are your comments. It will be useful for me to understand. Oh, okay. So if there's no questions, probably.
Yeah,
Okay.
I can probably ask a question on behalf of these students.
Yeah, okay, sure.
This regression some of them might be hearing for the first time. Is that the case? No. But we know the least square fitting. So regression is a more generic term for that. Can you please let us know whether the least square fitting is a special case of that and how?
Yes. Yeah, so least square fitting, as I said, least square fitting is because like normally when you're like during your BSc or maybe engineering, you actually describe this least square fitting, because as I said, that the way you are defining this residual, right, this error term. So basically you are actually taking the difference between your actual value and the predicted value, and you are basically getting the error in terms of the difference between that as a square, right? So that's why it's called solving the problem in terms of error minimization in terms of square of that error, right? And that's what is called a least square. So least square and straight line fitting or linear regression is same thing, right? But regression is little bit broader aspect or broader class, where actually you're not going to talk about a linear regression, but you're talking about non-linear regression also in terms of logistic regression, in terms of polynomial regressions, and in terms of Bayesian linear regression. So there are different linear regression, different kind of regressions are available. So regression is basically a super class, and least square is one of the class that is linear regression. Does it make sense?
Thank you. One more small question.
Sure.
Showed us that the method of pseudo inverse,
Yeah.
right? It is the same method which was discovered by the Roger Penrose.
Yes. 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 He is physicist. He is astrophysicist. I guess, right? And he got this year prize, right?
Do you know how,
Uh,
where did he apply it to? I don't know.
I think there is a specific paper like he wrote it is a mathematical paper rather than implementing on some physics problem. So he wrote as a mathematical paper first, as a proof and principle everything, and then people started to use that for some problem. So yeah.
Yeah, I think he applied it in his calculation somewhere. I'm not sure.
Everywhere you need to apply whenever.
But that is an assignment for these guys. Look for the application of pseudo inverse. Yeah, which was given by Roger Penrose and maybe another mathematician or something. But the same method he
Moore Penrose inverse. So
Moore Penrose. Yeah.
Yeah. So one of mathematician, one of the physicists, and
The matrix is non-rectangular.
Yeah.
Can you hear his comments? Can you be a little louder? Yeah, so he's telling us some reference.
Yeah, so go ahead and check for that. Like it is very, very well known like function or mathematical relation between how to handle some non-square matrix. So if you read any books in linear algebra, there it is already there.
Right. Are there any questions?
So I think I should ask one question. Like, is the speed is enough, fine enough, or I should be a little more slower, or how do I operate on that? Because I think this is the first time, so they are not might be open up on that part. But I think it is really crucial for me to understand.
No, I think it was fine. If they go through that Google Colab notebook, they will understand what has been taught. You did not cover too many things. That's fine. You explained too many things. I mean, you try to give us broad picture and if you use application everywhere. But the things you covered is simply a linear regression. Right? I think if they go through that Google Colab notebook, they will go. Speed is fine. There's no issue.
Yeah. Okay.
You also gave us the broad overview of techniques used in data analysis, especially the linear algebra method. Right?
Yeah.
Linear algebra is critical for physicists, those who want to do the data analysis.
Okay.
Yeah.
Yeah. Thanks for the feedback.
Thank you so much.
Yeah. And thanks all for joining today's session. Yeah.
Thank you.
Okay.
Thank you. So we'll see you tomorrow.
Sure.
And the last lecture for today will be at 3:30. So see you.
Okay.
Thank you, Amit.
Okay.
Thank you.
Okay. See you then. Bye bye. See you tomorrow.